Starting off with belt work first. It says the system of equations above has a solution x, y. And it says what is the value of x, and it is given us these two equations. We have 1/2 times the quantity of 2x plus y is equal to 21 divided by 2, 21 halves, however you want to look at it. And the second equation is y equals 2x. So if you remember from chapter 1 when we were discussing linear equations, you have three ways primarily to solve this. You could graph it. It's not necessarily the most efficient method and it's an estimation because it would take time for us to graph it. And this one actually comes out to be a decimal, so that's not really our cup of tea. We could use elimination. That one, once again, is going to cause us a little bit more work because elimination method is all centered around trying to get two variables, like an x in the first equation, and have it be the exact opposite in the second equation. So for y equals 2x, we would have to try to find to get a negative 2x up top, and we would have to multiply. So that one's not necessarily going to fit the bill either, but substitution. Substitution method requires you to solve one of the variables, okay, or isolate, and then we plug it in. So this one in the given form, it's already isolated for us. We know that y is going to be equal to 2x. So we're going to take this 2x and we're going to plug it in for this y, and then we're going to work off this top equation to try to isolate x. So once we plug it in, we're going to be dealing with 1/2 times the quantity of 2x plus 2x, which is equal to 21 halves. Okay, so now we want to start to isolate the variable. The first thing that we could do is we want to get rid of this 1/2. Since it's 1/2 times this quantity, we're going to divide by 1/2. Okay, or that's basically multiplying by 2. Anytime you're dividing by a half, you're essentially multiplying by 2. So we want to do that to both sides. So those are going to cancel out, and we're going to be left with 2x plus 2x is equal to 21. We'll combine our like terms to get 4x is equal to 21. And then we will divide by 4 on both sides to show that the value of x is equal to 21/4 or 5.25. Okay, so in the given format, it's pretty simple because they had already isolated a variable for us, and it's set up perfectly for substitution. You could, like I said, you could graph it, you could use the elimination method, but that requires a whole lot more work, and especially on a test like the SAT where it's timed, if we can use the most efficient method on an easier question, the more time we have to handle those harder questions. Okay, so today what you have on tap, we're going to be talking about transformations of functions. Okay, I addressed it a little bit while we were home before Thanksgiving break. You're going to see some similarities, but we're going to focus on three primary graphs. Y equals x, y equals x squared, and y equals the absolute value of x. We're going to talk about how they can be transformed to make other functions. But first, we have our 5-minute check. The answer is going to be 21/4 or 5.25 for the bell work. Okay, so first 5-minute check. We want to identify the type of function represented by the graph. Okay, you can see that the graph's up there. It is a discrete graph, so it is not continuous, and it has a jump. So if we just analyze our answer options, we have linear, which is a straight line, and linear functions are always continuous. Remember, we can draw any line without having to pick up our pencil. To draw that graph, we would have to pick up our pencil. So it can't be a linear function. Let's look at C. That's the graph of the absolute value. We're going to be talking about that a lot today. But remember, absolute value graphs are that V. They look like a straight V. Okay. And then, so our graph in the top right corner isn't a V, so it's pretty safe to assume that that's not going to be absolute. And then you have parabolic. Parabolic graphs are your U-shapes, with both ends either going off to a positive infinity or a negative infinity. So by the process of elimination, we can conclude that this is a piecewise defined function, because it can't be a linear function because it's not continuous. It doesn't fit the form of the absolute value, and it doesn't fit the form of a parabolic graph. So we're looking at piecewise defined. The second one says identify the function represented by the graph. Once again, we already talked about linear. So those are continuous functions that we can draw without picking up a pencil. This one is continuous, but it doesn't have a constant slope. So we can eliminate linear. When they're talking about quadratics, quadratic and parabolic are two terms that mean the same thing. Okay, you're always going to have that parabolic shape, that U, if it's a quadratic. So once again, that doesn't fit it. The greatest integer function is a function that we covered in 2.5, and that is our step function, where we have to round down to the greatest integer closest. So the graph up in the right-hand corner isn't a step function. It's not a linear function. It's not a quadratic. So once again, by just eliminating answer choices, we can conclude that this is an absolute value graph. Okay. Number 3 says the function f of x is defined by 5x if x is less than 8, 8.5x minus 1 if x is between 8 and 16, and 12x plus 4 if x is greater than 16. So looking at this format, this is going to be a piecewise graph. Okay, it's going to be a piecewise defined function, but we really got to pay attention to our domain. Okay, and it says the function f of x gives the amount of money earned for working x hours. So how much will an employee earn for working 12 hours? So to solve this, it boils down that we got to find which area of the graph we fall based upon the domains. So is 12 less than 8? No, so we're not going to be using 5x. Is 12 between 8 and 16? Yes, so we're going to be using that 8.5x minus 1. Okay, and all we're required to do is plug 12 in for our x value. We'll solve it, and we'll get the value of f of x. So we have 8.5x minus 1, and we're plugging 12 in, so that's 8.5 times 12 minus 1. 12 times 8 is 96. Yes, 96 plus another 2, so 8.5 times 12 is 92, minus 1, no. 8.5 times 12 is 102, minus 1 to get $101 for a 12-hour shift. That's where we should be looking. And that corresponds to answer B. Okay, like I said, piecewise functions, they're not really hard to work with. We just have to pay attention to the domain. So we really wanted to make sure that that we're selecting the correct function as listed by the domains of our piecewise function. And then it's just plug it in, carry out your order of operations, and solve it. So there's your 5-minute check. Okay, so we've previously analyzed and used relations and functions. What we're going to be talking about today, it says we're going to identify the effects on the graphs of functions by replacing f of x with f of x plus k and f of x minus h for positive and negative values. More or less to sum that up, that top objective is going to be a vertical translation or horizontal translation. And then identify the effect on graphs of functions by replacing f of x with a times f of x, f of ax, and a negative a of fx, and f of negative ax. to sum that second objective up, those are your dilations. That's what makes your graphs really skinny or really obtuse, we'll say. So your new vocabulary. We have parent graph and parent function. Okay, parent graphs and parent functions are, each graph has a family. Like x squared and 3x squared are part of the same parent. They have the same characteristics, so they function the same. The parent graph is the simplest form. Okay, we have the quadratic function, which is for x squared. We have translation, which is a slide of the graph around the xy coordinate plane. We have a reflection, which will typically be mirroring it over the y-axis or the x-axis. Okay, and then you have a dilation. Dilation means we're going to stretch it or compress it, okay, based upon the value of a. All right, so looking at some of the parent graphs, this is where we have to start if we're going to be talking about translations. Like I said, we're going to be talking about linear functions first. We're going to talk about quadratics, and we're going to be talking about the absolute value function. So, for a parent graph, for every linear equation, it all starts off where f of x is equal to x. Okay, and this is the simpler form, but there is what's known as the general format. Okay, the general format for any graph is that, call it g of x, is equal to a times f, yeah, like that, a times the f of x minus h plus k. Okay, where a is your dilation factor, h is your horizontal translation, and k is your vertical translation. Okay, so once again, a is the values that's going to stretch or compress our graphs. H is the value that's going to slide it along the x-axis, and k is the value that's going to be sliding it on the y-axis. Believe it or not, this written this way is actually in this format. It's just in mathematics, we like to remove redundancies. Okay, so this parent graph, f of x is equal to x, which is just a linear function. If we were to write it in this format, it would be that f of x is equal to 1 times the quantity of x minus 0 plus 0. Okay, and if you look at it, it sets up kind of an inside-outside thing. Anything added to the outside is your vertical translation. Anything added or subtracted on the inside is your horizontal. And then your dilation factor, if it's anything different or if it's omitted, is just 1. Like I said, we like to remove redundancies because x minus 0 is still just going to be x. 1 times x is still just going to be x. And then x plus 0, again, is still just going to be x. So in mathematics, we alleviate the 1, we alleviate the 0, and we alleviate that 0. And express it as this way. Certain characteristics of this graph. Okay, the y-intercept. Is equal to 0. Okay, the x-intercept is equal to 0, meaning that it crosses at the origin. Okay, this point, the y and the x-intercept being at 0, is very handy for you to find your horizontal and your vertical translations because that's sliding the graph back and forth. Okay, the slope, since it's just x, is equal to 1. So again, this is a linear function. So for the parent graph, it's always going to cross through the points 1, 1, and negative 1, negative 1. So if we were to continue this out, our parent function would look something like this. Okay, using most using most or linear functions, when you're talking about translations, your horizontal and your vertical translation really kind of correspond to the same thing. They're most commonly expressed in vertical terms. Okay, that graph gets slid up and it gets slid down. If you're talking about a dilation of a linear function, which is done by A, that's a change in the slope. Okay, so if we were to compare f of x, which is equal to x, to use a different color, say we'll compare it to f of x is equal to 2x. Okay, that's a dilation of 2, so it's stretched up. Our slope has changed. So instead of crossing through the point 1, 1, we're going to cross through the point 2, 1, and negative 1, negative 2. So our graph has been stretched. Okay, if we were to change the intercept or add on a constant at the end, that's what slides the graph up and down. So all your linear functions, you typically have a vertical translation and a dilation depending upon what the slope is. Okay, and once again, that's based upon A and K. Okay, that's the first parent graph that we're going to look at. Give you a second to make notes of those. Or I get too carried away. Okay, so looking at our next graph, or our next parent graph, we get that. The next one is f of x is equal to x squared. Once again, this is where all of your parabolic or your quadratic graphs stay. Okay, if we wanted to write it out in the general form, so again, it would still be f of x is equal to 1 times the quantity of x minus 0 squared plus 0. So no horizontal or vertical translations because it's just 0. And then 1 times x is always going to just be x. So x minus 0 squared is x squared times 1 is x squared plus 0 is still just x squared. But like I said, in mathematics, we alleviate redundancies. So that's what this would look like if it was expressed in the general form. And you're going to find certain consistencies with all of these parent graphs. Okay, the y-intercept is still at 0. The x-intercept still at 0. So all of these graphs were parent graphs that cross at the origin. Okay, this is a parabolic, so there's not really a slope. Okay, but most common points that this hits, if I just build a little table using -2, -1, we already discussed that 0, 0, 1, and 2. Okay, if we were to plug -2 in, -2 squared gives you 4. -1 squared is going to give you 1. 1 squared is going to give you 1. And then 2 squared is going to give you 4. Okay, once again, these help you if you can readily identify them. 1, 2, 3, 4. These help determine your dilations and they help determine the sliding. Okay? And your translations are parabolic right there. Your translations, the easiest way to determine if this graph has been translated is where does that vertex fall? Okay, if it's shifted to the right or is it shifted to the left? Okay, if we can find the vertex, we know if it's been translated. Okay, also vertically. So horizontally and vertically is dependent upon the vertex. Where does that fall? Okay, your dilations are a little bit harder to find. Once again, that's what stretches or compresses the graph. Okay, so if we were to compare it to, where did I put that good red marker? If we were to compare it to, call this one g of x, we'll set it equal to 2x squared. And we build the same points. Okay, negative 2 squared is 4 times 2 is going to give you 8. Negative 1 squared is 1 times 2 is going to give you 2. 0 squared is 0 times 2 is still 0. So you can see the origin hasn't changed at all. 1 squared is 1 times 2 is going to give you 2. 2 squared times is 4 times 2 is going to give you 8. So you can see the dilation has been bumped up. So we're still at the origin, where we're going to be crossing through the points 1, 2, and then 1, 2, 3, 4, 6, 7, 8. Okay, and you can see that our graph is a little bit skinnier on the red side. Okay, and that's because it's been expanded vertically. You might ask yourself, what happens if the value of A, or the absolute value of A, is less than 1? Okay, that compresses the graph. So this A value, if the absolute value is greater than 1, it stretches it. If it's between 0 and 1, or a decimal or a fraction, it's going to compress it. And that's true for all of your graphs. So instead of being at negative 1, 1, we'd be at negative 1.5. And then we'd be at negative 2, 1, because we would have to multiply it by 0.5. Once again, you want to find the vertex for any translations, whether it's slid vertically or horizontally. And then you want to compare points based upon these 5 points to try to determine what our dilation factor is. A couple seconds to copy that one down. Okay, and the final parent graph that we're going to be talking about is f of x is equal to the absolute value of x. Okay, absolute value, once again, it's that v. So if we were to put it in the general form, to write it, it would look like g of x is equal to 1 times, that's a terrible one, I'll have to change that, 1 times the absolute value of x minus 0, just going to be x, plus 0. And I had to alter my 1 because I draw like lines. So once again, x minus 0, 0 takes the absolute value, multiply it by 1, and then add 0 is just going to be the absolute value of x. So that's your parent graph in the general form. Okay, so your key points. Once again, the y-intercept is equal to 0. Your x-intercept is equal to 0. Okay, so all of your parent graphs cross through at the origin. Once again, we want to use that to determine whether the graph's been moved up, it's been moved left, right, or down. Okay, this one does have a slope, but it has to be broken in 2 different portions. So the slope, okay, if the value of x is less than 0, the slope is -1. Okay, meaning that it's coming down. Still going to touch the point -1, 1. Okay, if the value of x is greater than 0, the slope is a +1. And that's what gives you that v. Okay, so trying to determine a dilation on the absolute value function, we can take the slope of either one of our sides, and that's going to give you the dilation factor. Okay, some key points that this graph will always cross through. I'm going to write them right here. It'll be -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. Okay, constant levels of increase. If we wanted to talk about a dilation, and I'll do this one as a decimal, and we wanted to look at, say, g of x is equal to 0.5 times the absolute value of x, that's going to compress it because our value of a is less than 1, right? So instead of going through -2, 2, it's going to go through -2, 1. It's going to go -1.5, still going to be at 0, 0, because we haven't slid it anywhere. I have to continue my table on the other side. It's going to touch the point 1, 0.5. It's going to touch the point 2, 1. Okay, and looking at that graph, it's going to look something like this. Okay, and that's because our dilation factor, since it was 0.5, it's really compressed that graph down. So it makes it look a little bit more obtuse. Okay, and all of these characteristics, especially the general form, you can find that on page 128 of your book. There's a nice table, which I'm going to bring up right now. Okay, and this is all on page 128. So again, it basically just summarizes everything that I just said. So you can see the general form. G of x is equal to a times f of x minus h plus k, where f of x is the parent function. So all of these translations, we begin with that parent function, and then we move it, we stretch it, we compress it, or we reflect it. Okay, the absolute value of a stretches or compresses. Okay, so when the absolute value is greater than 1, the graph of f of x is stretched vertically. And if the absolute value of a is between 0 and 1, the graph is compressed vertically. Okay, and that's true for all of your graphs. Linear functions, parabolic functions, quadratic functions, cubic functions, absolute value functions, step functions. That's what that value of a does. It stretches it or it compresses it. Okay, the vertical translation, the value of k on the outside. That's why I say it sets up an inside-outside. If k is greater than 0, the value is translated k units up. So it's like taking f of x is equal to x plus 2. It's the same slope, it's just shifted up. Okay. If the value of k is less than 0, the graph is translated k units down. Okay, so that would be like f of x is equal to x minus 2. So plus or minus on the outside here. The horizontal translation one is really the one that kind of throws most people for a loop. And that's because we always forget that the general form is x minus h. So if we see a minus here, that means that we're shifting the graph to the right. Okay, we're shifting graph to the right. And that's if h of 0 is equal to, if h is greater than 0, the graph of f of x is translated h units to the right. So we have to remember it starts off with a negative. So it's like minusing a positive number. See a minus on the inside, we're translating it to the right. If we see a plus on the inside, we're translating it to the left. Okay? And the last one is that the reflection. So if A is less than 0, the graph of f of x is reflected in the x-axis. Okay? Or where the x-axis is our line of reflection. So I left the absolute value function up there. Okay, if we wanted to graph to illustrate the reflections, I'll do it in red again. So if we said that g of x is equal to the negative absolute value of x, notice it didn't stretch it because the value of a is still 1. So it's still just that base parent graph, but it's a negative 1. What that does is it flips it over the x-axis. So our graph is going to have the same slope, but instead of pointing up, it's going to be pointing down. Okay, and that's true for all of your parabolic functions and your linear functions. Okay, and you can see that, and I'll do the linear function. Where in black, we'll have the parent graph of f of x is equal to x. And in red, I'll do f of x is equal, or g of x, keep them consistent. G of x is equal to a negative x. Okay, so our parent graph crosses through the origin. There's no vertical or horizontal translations. There's no dilation. It's just flipped over the x-axis. Like so. Where in red you have f of x is equal to a negative x. So what was in quadrant 3 is now in quadrant 2. And then what was in quadrant 1 is now in quadrant 4. So that's what that negative does. It flips it over the x-axis. Okay, where your x-axis is the line of reflection. And so it's kind of like looking at symmetry. All right. Let's get back to the slides. Okay, first example says to describe the translation in y equals x plus 1 squared as it relates to its parent graph, and then graph the function. So here, remember that we have, this is going to be a horizontal translation where the parent graph is equal to f of x is equal to x squared. Okay, but what does that plus 1 do? So it's on the inside, so that corresponds to a horizontal translation. Remember, if the inside is a negative, so if it was x minus 1, shift it to the right. If it's x plus 1, it's going to be shifted to the left. Okay, if we analyze the dilation factor, which would be right out front of these parentheses, it's still 1. Okay? And if we look at a vertical translation, that's going to be plus 0. So the graph isn't moved up or down. It's not stretched by any means because a is equal to 1 and k is equal to 0. It's just that value of h. It's minus -1. So knowing what we know about x squared, that should cross at 0, 0, and it's shifted left 1, the graph of x plus 1 squared is going to be shifted to the left. So our origin has now moved to -1, 0, and all of its associated points have been moved as well. So we used to cross through 1, 1. Now we're going to cross through 1, 0. It was -1, 1, and now it's going to be -2, 1. Okay. Now it's going to go through 1, 4. Now it's going to go through -3, 4. Just like that. Okay, so that graph has just been shifted to the left because it has that horizontal dilation or a horizontal translation factor of -1. So it's shifted 1 unit to the left. No stretching, no nothing like that. It's just shifted. So in the function y equals x plus 1 squared, the value of h, the horizontal factor, is equal to a -1. That's what causes it to be a plus, because anytime you're subtracting a negative, it really turns into a positive, or really turns into plus a positive. Okay, and since we have that factor of -1, it's moved 1 unit left. So every point on the graph of y equals x squared moves left 1 unit. So graph the vertex at -1, 0, which was formerly at 0, 0, and sketch the parabola. So that's what it looks like. Because x squared should start here. Since it's 1 left, it's going to start at -1, 0. Okay, so now let's talk about this one. If we look, our value of a, the absolute value is still 1, so it hasn't been stretched or compressed at all. The value of h is 0, so it hasn't slid horizontally at all. The value of k is still 0, so it hasn't slid vertically at all. It just has a reflection because the value of a is negative. So remember, if its value of a is negative, that flips it over the x-axis. So we use our critical points that happened on absolute value of x. The origin hasn't changed, so it's still at 0, 0. Used to go through -1, 1, but now it's going to go through -1, -1, 1, -1. So that's what our graph is going to look like. We have to remember that the absolute value function and those little brackets are treated like parentheses. So if there's a plus or a minus on the inside there, we want to take advantage of that. Okay, we have to take that first, and then we would multiply by the dilation factor, and then we would add by the vertical translation factor. So we always take care of what's on the inside first, according to our order of operations. They're treated like parentheses. So we handle that first. So in the function y equals a negative absolute value of x, the function y equals the absolute value of x is reflected across the y-axis or the x-axis. Like I said, there's no horizontal translation, no vertical translation, there's no dilation. It's just simply a reflection. So graph the vertex of the absolute value function at 0, 0, and point the graph downward. looking just like that. Okay, here we have a dilation. I actually did this when we were talking about the parent graphs. So if we look, the value of h in the given equation is still 0. This is x plus 0, absolute value of x plus 0. Value of k is still 0. It's not slid anywhere. But we have that 1/2. So we would take, and we could build a table on this one to emphasize the point. So y is equal to 1/2 times the absolute value of x. So if I use the points -2, -1, 0, 1, and 2 for my x values, if I plug in -2, I have to take the absolute value first. So the absolute value of -2 is 2 times 1/2 gives you 1. -1, the absolute value of -1 is 1 times 1/2 is 1/2 or 0.5, however you want to express it. The absolute value of 0 is 0 times 1/2 is still going to be 0. Because anything times 0 is 0. Absolute value of 1 is 1 times 1/2, 1/2. Absolute value of 2 is 2 times 1/2 is 1. So these are my critical points. Okay, so since my value of A is at less than 1, it compresses that graph. So I cross at 2, 1, right about there, right about there, right about there. And we would describe this as being compressed vertically. Some people might describe it as being stretched horizontally, but in the grand scheme of things, though, you're saying the same thing. If you're compressing it vertically, you're stretching it horizontally. Or if you're stretching it vertically, you're compressing it horizontally. It's two different ways to say the same exact thing. But the key with the absolute value function, like I said, we want to treat those brackets as if they are parentheses. Okay, we have to take care of any operation that occurs on the inside of those first. This one, there's no plus or minus, so we can just take the absolute value of x. So since a is equal to 1/2, means the function is compressed vertically by a factor of 1/2. So we graph the vertex and the absolute value function, and that's a misprint. That should be compressed the graph vertically instead of stretch. We'd only stretch it if the value of the absolute value of A is greater than 1. So you can see it's been compressed vertically. 0, 0 still is the vertex. 1, 1/2, 0.2. If the x value is 2, the value of y is 1. -2, the value of y is 1. -1, 0.5. So it's compressed vertically. That's because we have a fraction in A. Okay, so this one, they are stating, this is where I don't necessarily like these questions, because they want you to assume that that graph is the parent graph. Okay, the graph that's listed. If you look at that, we can clearly see that if we were comparing it to the absolute parent graph of x squared, that graph has been flipped over the x-axis, so it has a negative a value. It's been slid 5 units to the right. It's been slid 12.5 units up because our vertex is no longer on 0, 0. Okay, and it looks like it has been stretched vertically. But we have to be careful about what the question is asking us. Okay, we're not comparing this to x squared. You know, we can identify all those characteristics. It says the graph of f of x is shown on the grid. If the graph of f of x is translated 3 units to the left, so I want to go left 3. Okay, it's translated 1 unit up. So we want to go up 1. and reflected in the x-axis to create the graph of g of x, which function best represents g of x in terms of f of x? So what this is really asking you, after we sort through all of the information, is how can we write it in a general form that would get all of these translations and reflections done? Okay, so we compare that to our general form. So, first one, and it has to be in terms of f of x, and we're writing g of x. So we're going to have g of x. Okay, first it was reflected in the x-axis. Remember, the reflection from the x-axis occurs when we have a negative a value. Okay, so we want to have a negative out front. Okay, if it was a dilation by a factor of 2 or a factor of 3 or a factor of 1 half, we would put 1, 2, 3, or 1 half. But it doesn't specify that in the question. It just says that it's reflected. So that's a negative f of x. Okay, so we've taken care of that one. We want it to translate 3 to the left. So remember that's an inside. So it's going to be plus 3. Because anytime we have a plus on the inside, we're moving it to the left. If it's a negative on the inside, we're moving it to the right. Okay, so that takes care of that. And then we want to translate it up 1. Okay, so that comes from the value of k. And remember, if that's plus to positive k, it moves up. If it's a negative k, it moves down. So we can express that as g of x is equal to a negative f of x plus 3 plus 1, where a negative is our reflection, the plus 3 moves it left 3, and the plus 1 moves it up 1. Okay, so we want to use that general format to alter f of x so that we accomplish what the question states for g of x. So we have to be very selective about what we're reading, and we have to be detailed. Okay, we can't just fly through it. We have to really break it down and see what the question is asking us to do, because it can get pretty tricky sometimes. So we're multiple choice. We want to select the answer of what we had. Okay, and that should correspond to answer A. So we have the negative, which causes the reflection over the x-axis. The plus 3 moves it left 3. The plus 1 moves it up 1. Oh, let's get some light back in here. All righty. So that is your translations of functions. Remember, it all starts with the parent graph. Parent graph is the simplest form. And then we alter that parent graph. We slide it. It's translation. We move it up and down. Translation again. We stretch it or dilate it, or we reflect it. Okay, at this time, you can go and begin working upon your homework. I'm going to leave the Zoom call running. That way, if any of you have any questions, your homework problems come from page 129, 2 through 30, and it's all the even problems. Okay, and it's going to be handling those processes the exact same way we just did.